Hello, my name is David. Welcome back to Organic Chemistry. Today we're going to be discussing alkene nomenclature and properties, the things you need to know about them to succeed in organic chemistry. Okay, so the first thing we're going to be talking about is degrees of unsaturation. Now, in doing so, you want to hit on these two different points, the CnH2n, that formula, and the CnH2n plus 2, that's the alkane formula. These will be handy when we get into the practice problems. Another thing you'd like to remember is this. There's the textbook way, and then there's this way. Halogens are equal to hydrogens. You'll see how this plays out. Oxygens are negligible, and nitrogens act as if they are another hydrogen. This is very important when we get into the practice problems. There's also the textbook degrees of unsaturation formula. Andrew likes to use it. Me, personally, I like to use the memorization technique, the small, easy technique that I prefer over it. And so let's get into some practice problems. C4H8Br2. So if you want to pause it, go ahead and go for it, but I'll get right into it. So Br2, we said that halogens are equal, they're assimilated to hydrogens, so therefore we can easily just do, you can put quotes around this because technically this isn't the actual molecular formula, but I like to write C4H10. You can put some parentheses or quotes around it because that's not really what it is, but that's what we're assimilating it to be. And so to find the degrees of unsaturation, this is an important this is the important first step of that problem. And so you want to relate back to that CnH2n plus 2, the alkane formula, to find the degrees of unsaturation. Plug in the values, C4H24 plus 2, and you get C4H10. So you may be like, what is this? Simple. No degrees of unsaturation. Now the next problem, C6H5NO2. Do the same exact thing. No halogens in this one. So it's a little bit different. Oxygens are negligible. N, nitrogen, is as if you are adding another hydrogen, which is different than the last one. So it's going to be C6H6. Now you want to go ahead and calculate the degrees of unsaturation using the alkane formula. You may put the quotes around it if you'd like. CnH2n plus 2. Plug it in. Two 6 plus 2. Run in the formula. C6 H12 plus 2, 14. And then from here, you can subtract 2's, but we know that the quoted formula is C6H6. So to get to C6H14, you got to add 8. And so therefore, the 8 divided by 2 is 4. You have 4 degrees of unsaturation in this practice problem. We'll get right into this. C8H28 plus 2. We know that we can add these chlorines to the hydrogens as if they are just extra hydrogens. So literally pretend that this is like H3 and then just add it in. So C8H12. That's our quoted formula. That's how I like to think through it in my head. There's different little ways. Everybody has their own thing, but this is my way. You may use it if you'd like, or you can use the textbook formula. So C8 H18. Calculate the degrees of unsaturation. 18 to 12. What do you do to get there? Subtract 6 divided by 2. I say subtract 6 and then the divided by 2 because For each bond, there's 2 electrons. Each atom shares an electron, and that's why it's 2. And so for this problem, there's a difference of 6 divided by 2, meaning there's 3 degrees of unsaturation. I hope that helped. Let's get into some pi bond nature. Okay, so this is just a simple ethene molecule. I'll draw in the hydrogens to make it easier. Just on this atom. And so what we're seeing here, this may be foreign to some people, it may not. In Gen Chem, we discussed VSPER, VESPER, the electron theory, and then we also discussed molecular orbital theory. I'm not going to touch on these in this video because that's a whole different topic. We'll get into that in another video. But what we need to know for pi bonds is that they follow on the sigma bonds. So you can't have a pi bond without a sigma bond. You can have a sigma bond without a pi bond, though. A sigma bond is just a simple single bond. And so what we can see here, we'll work on this carbon atom, is that we have these vacant unhybridized p orbitals. And so what these are going to do is lateral overlap with the following carbon atom and their vacant p orbitals. Now, why is there a vacant p orbital? It's because we have this carbon. We know that double bonds, or carbons with 3 bonds, carbons with 3 different bonding domains are sp2 hybridized. Hydrogens, not so special. They experience just that simple S hybridization. Carbons have sp2 hybridized orbitals, and this is that sigma bond. In this instance, this pi bond is formed from the lateral overlap of the unhybridized p orbitals, and that's where the pi bond arises. Now, in organic chemistry, something very important to note in this topic is that pi bonds are extremely nucleophilic. Okay, so we have these vacant unhybridized p orbitals. They undergo lateral overlap. That's what the white line is for, but I just drew it for the sake of it. And that's where the pi bond arises. Pi bond, one extra pi bond over the sigma bond is a double bond. And when you have a second pi bond on top of that, that'd be a triple bond. For a triple bond, obviously, you would have to get rid of this hydrogen domain or this domain, because a carbon that has a triple bond is sp hybridized. Now, these bonds, pi bonds, make the carbon atoms very nucleophilic, meaning they're going to attack electrophiles. And that's very important in later topics that we're going to discuss. So, with that said, stability arises. Now we're looking at the cis isomer here. We'll get into it in a later topic, but that is known as Z geometry, Z same side, which is a topic that is very important when naming molecules. When you have big molecules that have multiple double bonds, you don't want to have to write cis in front of every bond. It makes it so that, say, this is carbon 2. You want to be able to say at carbon 2, it is Z geometry, or at carbon 2, it is E geometry. It's very important. It also just makes it less tedious, honestly. And so in this one, we're looking at the trans isomer. Now, this is going to be more stable than the cis isomer due to steric strain. Think about putting 2 positive magnets, holding 2 positive magnets in your hands and trying to get them as close as they can together. They're going to repel. And so that's what you experience when you're looking at a cis isomer. The nuclei of these carbon atoms and the hydrogen atoms in particular, they undergo this steric strain. They don't want to be in each other's space. And so with double bonds, we have a simple little stability ladder, you may say, that increases with substitution. Meaning, in layman's terms, the more R groups you have, the more stable it's going to be. And then throw trans isomers and cis isomers in there. Trans isomers are going to be more stable than the cis isomer. All right, so just let's run through the ladder real quick. We start with the ethene. We're going to go to a monosubstituted. From the monosubstituted, we're going to go to the disubstituted cis isomer because it is less stable than the trans. We're going to make it to the trans isomer. Notice the two groups, opposite sides of the bond. Tri-substituted. Tetra-substituted. Or fully substituted. This is going to be that most stable. This is going to be the golden ticket. All right, so lastly, we're going to end with nomenclature. Let's get right into it. It's the best way to learn nomenclature simply by doing practice problems. There's no easy way around it. Get right into the practice problems. So, carbon 1, carbon 2, carbon 3, carbon 4. You always want to place the alkene at the lowest carbon possible. And this also, when you have an alkyne, we'll get into this in a later video, but alkynes and alkenes practically when naming are similar, meaning they really don't outweigh one another. It just depends on which carbon they lie on. You want to place the alkene or the alkyne when naming on a lower carbon. And so 1, 2, 3, 4. This is going to be 1, 4 carbons, meaning bute, ene. It's as easy as it gets. All right, let's get right into it. Do we start from the left side or from the right side? We start from the right side because of that hydroxyl group. It has higher priority than the alkene bond, or the double bond, may I say. 1, 2, 3, 4. The alkene gets the parent name followed by that all. So let's write this as 3 bute, because it's a 4 carbon, ene, 2 all. 3 butene, 2 all. All right, so let's get into the next example. We got the chlorine atom on, which side do we number from? This side. 1, 2, 3, 4, 5, 6. Now, if there are other substituents on this molecule, say an ethyl group, 2 carbons, which one would go first, the chlorine or the ethyl? Because of alphabetical order, the chlorine atom would be stated first. But it's not here, so let's get right into it. 3 chloro. Because this is a conjugated system, it is a more stable molecule. We'll get into this in a later topic. We'll not discuss it now. But it is 1, 3, 5. 1, 3, 5. 6 carbon chain. Hexa. Triene. Very important. All right, so let's hop into a little more tricky problem. Where do we number from? Now this is tricky. You may be looking at it and you may say, this is how we number it. That'd be wrong. You may say, we can start from this side. That would also be wrong. The best way to number this is 1, 2, 3, 4, 5, 6, 7, 8. 8 meaning it's going to be oct. There's a methyl here and a methyl here. So that'd be dimethyl. So how do you name this? We get a methyl on the second carbon, a methyl on the fifth carbon, 2,5, dimethyl. It's extremely important to make sure to include those prefixes. It's extremely important. Dimethyl. 1, 4, 7-octatriene. Awesome. Let's hop into the next one. All right, so this is going to be the last practice problem. This one's tricky. Let's hop into it. We have a chlorine atom. It's always important to knock off those substituents. Figure out which is the longest carbon chain. These are all things Andrew touched on in the first video. Find those substituents, find the longest carbon chain, prioritize the substituents, and name it. Got a methyl here, an ethyl there, hydroxyl group here, and an alkene. Wow, how do we name this? Let's first number it. 1, 2, 3, 4, 5, 6, and 7. So this is hept. Very important. And there's a double bond present. So that's going to be part of that name. And there's an alcohol. We already did an alcohol. So we know that there's going to have to be an all after that. 1 hydroxy. We got a 4-methyl, 3-ethyl, 5-chloro. Where do we start? 5-chloro because of alphabetical order. So due to alphabetical order, what's going to follow this? It's going to be the ethyl group. And so on and so forth. So 4-methyl would follow this. Ethyl, 4-methyl. 3 indicate that double bond. Very important. Leave the E off the end, meaning there's more to the molecule. 1 all. 5-chloro, 3-ethyl, 4-methyl, 3-hepten, 1 all. Thank you so much for watching. We'll get into some reactions of alkenes, some reactions, synthesis of alkynes. Hope you stick around. Thank you. See you in the next one.